In this video, we'll look at how we can classify different kinds of enthalpy and then try out a few calculations that combine stoichiometry and enthalpy. Before we explore how to calculate enthalpies, it's worth doing a quick classification. Every single chemical reaction that occurs has an enthalpy of reaction, a change in energy as the reaction occurs. This is because if a reaction is occurring, then somewhere bonds are being broken, which absorbs energy, and made, which releases energy. Usually the enthalpy will be expressed in kilojoules of energy released or absorbed per mole of reactant. Because we can classify different kinds of reactions, we can also classify enthalpies for these reactions. For instance, if you're measuring enthalpy for an acid-base reaction, in which the acid and the base neutralize each other, you would call it an enthalpy of neutralization. And if you are measuring the heat released when fuel is burnt, you would talk about an enthalpy of combustion. These two examples can also be classified simply as enthalpies of reaction because they are chemical reactions. However, we have some other enthalpies that are not so obvious. When a substance is dissolved in a solvent, there is an energy change associated with that too, since as the solid dissolves, the bonds that hold the atoms or molecules or ions in a solid are broken, and new bonds are formed with the surrounding solvent molecules. Most enthalpies of solution are fairly small, and you don't notice them on a day-to-day basis, but there are some compounds which have large enthalpies of solution and can produce or absorb a lot of energy. Lastly, there are enthalpies that relate to physical processes rather than chemical processes. These enthalpies are sometimes called latent heats. When you melt a solid, the attractions that hold the molecules in solid form have to be broken so the molecules can move freely as a liquid. This requires energy. In the opposite direction, when a liquid freezes, energy is released as the attractions are forming between molecules and they're locked in place as a solid. This means that melting is an endothermic process. It needs energy to be put in. Think of warming ice up to melt it. And freezing is an exothermic process. That freezing is exothermic may seem counterintuitive because we put things in the freezer and make them cold in order to freeze them. But in fact, the very purpose of making them cold is to suck out that heat from the exothermic process so that the molecules can form the bonds and become solid. So, we're going to try a couple of problems that combine enthalpy with stoichiometry. The first one will be one involving enthalpy of solution, and we're going to use an enthalpy value for a dissolving reaction, also called a dissolution, to work out how much energy is absorbed or released when something is dissolved in water. And in the second problem, we'll look at an enthalpy of combustion, and we'll use an enthalpy value and an energy value to work out how many moles of a fuel were burnt. And then we'll use stoichiometry to work out what mass of oxygen was needed to make this reaction happen. So let's try a problem to do with enthalpy of solution. I have a reaction equation here. On the left you can see we've got ammonium chloride solid, and on the right of the equation I'm showing the two ions that the ammonium chloride is made up of, the ammonium and the chloride, and they're both shown with the subscript aqueous, meaning that the ammonium chloride solid has dissolved in water, the ions have separated, and we now have an aqueous solution of ammonium chloride. And you can see that that has an enthalpy associated with it. It's 14.78 kilojoules per mole. So if I dissolve 1 mole of ammonium chloride, then the energy change will be 14.78 kilojoules positive. So that means that it's an endothermic process. And the question we've got is, what will the energy change be if 45 grams of ammonium chloride is dissolved in water? So our strategy is this. The first thing we have to do, we have a mass of ammonium chloride and we have to convert that to moles. So we're going to calculate the moles of ammonium chloride that we have present. And the second thing is we will then use the relationship that enthalpy equals energy over moles to solve for energy, because we have an enthalpy value and we will have a moles value. So let's try that out. So first of all, we know that we need to convert mass to moles, so we use our molar mass equals mass over moles relationship. And because we're looking for moles, we're going to rearrange that to make moles the subject of the equation. And we know then that we have 45 grams, so that will go on the top. And we need to calculate the molar mass of ammonium chloride, and you'll find that it is 53.5 grams per mole. And when we do that calculation, we find that that gives us 0.841 moles of ammonium chloride. Okay, now we know the moles of ammonium chloride, and we also have a value for the enthalpy of dissolution. So we can use the delta H equals delta E over moles relationship and rearrange it so that the change in energy, delta E, is the subject. And we find then that all we have to do is multiply the enthalpy, 14.78 kilojoules per mole, by the number of moles that we have present, which is a little under 1 mole, 0.841. And when we calculate that out, we find that it is 12.43 kilojoules. Now, 12.43 kilojoules has 4 significant figures. We should look back at our calculations and find the value that has the lowest number of sig figs. That's the 45 grams, the mass of ammonium chloride. And we need to round that down to 2 sig figs, so that gives us 12 kilojoules. We also should note that the original enthalpy value is positive, and that means that this energy change will be plus 12 kilojoules, which means that the system, the reaction, is absorbing that much energy from the surroundings. So that means that it's an endothermic process. Now let's look at a different reaction, a combustion reaction. Here we're going to burn methane in oxygen to give carbon dioxide and water. The enthalpy of reaction this time is minus 890 kilojoules per mole, and that means that if we run this reaction as written, that is with 1 mole of methane and 2 moles of oxygen, we will get 890 kilojoules of energy out. It's exothermic. That means that the enthalpy of combustion of methane has the same value. So remember, this was the enthalpy of reaction. The enthalpy of combustion of methane is essentially the same thing. We burnt 1 mole of methane and we got 890 kilojoules out. So delta H combustion of methane is minus 890 kilojoules per mole. Note that enthalpies of combustion are defined for 1 mole of a specific fuel. However, if we were instead interested in the energy as a function of the amount of oxygen that was used, we would have to do an adjustment. 890 kilojoules of energy is released for every 2 moles of oxygen used in this process, so the enthalpy value could also be expressed as delta HR, the enthalpy of reaction with respect to oxygen, would be 890 divided by 2, so that's minus 445 kilojoules per mole of oxygen for this reaction. We wouldn't call this the enthalpy of combustion of oxygen, since the oxygen is not combusting. It is what is needed to make the fuel combust. It's what's called an oxidizing agent. More on this when you do redox reactions. Here's another combustion example, ethane gas burning in oxygen. Notice that this balanced reaction has 2 moles of ethane reacting with 7 moles of oxygen. When we run this reaction with those amounts of reactants, we measure 3,120 kilojoules of energy being released. So what is the enthalpy of combustion of ethane? Well, 2 moles of ethane produces 3,120 kilojoules of energy when it reacts. So the enthalpy of combustion of ethane is 3,120 divided by 2. That is minus 1,560 kilojoules per mole of ethane. And if we wanted to know the enthalpy of reaction relative to the oxygen, we could easily calculate that also. So let's try a problem using that methane equation. We burn some methane and we measure that 12,600 kilojoules of energy are released. First of all, let's try and calculate how many moles of methane must have been burnt to produce that much energy. And secondly, what mass of oxygen would have to have been used in that reaction. So let's take part A first. This is a problem that's going to use the enthalpy relation. So enthalpy is energy over moles. And we already have values for the enthalpy, and we also have a value for the energy that's released. And what we're going to calculate is the number of moles of methane that must have been burnt. So we rearrange the relationship so that moles are the subject of the equation, and that gives us moles equals change in energy over change in enthalpy. We substitute in 12,600 kilojoules for the energy and minus 860 kilojoules for the enthalpy. And then we pause for a second. If we divide a positive number by a negative number, we're going to get a negative number. And I'm really not looking for a negative number of moles. That would be weird. So what have we done wrong? Well, the 12,600 value that we put in for the change in energy, it was specified in the question the 12,600 kilojoules of energy were released. That means it's exothermic. The energy is coming out of the system. So that means we need to put a negative sign in front of the 12,600. Now we have a negative divided by another negative, and we find that the answer is 14.16 moles of methane. We should round that off to 14 moles because our enthalpy value is to two significant figures. So we've got 14 moles of methane were burnt to produce that much energy. All right, in part B, we need to use what we already know to figure out how much oxygen was used. And this is a simple stoichiometry problem. So we know that the molar ratio of methane to oxygen from the equation is 1 to 2. We know that we have 14.16 moles of oxygen. Remember that because I'm only part way through this particular calculation, I'm using the longer version of the number of moles. I'm not rounding off early. I will round off again when I get to the end of this particular calculation. So 14.16 moles of methane, we need twice as much oxygen, so that's 28.31 moles of oxygen. And then we simply use the mass-mole relationship to work out how much that weighs. So we get that the mass of oxygen equals the molar mass times the number of moles. You can work out for yourself that the molar mass of oxygen is 32.00, and we'll multiply that by 28.31. And that gives us 906.1 grams of oxygen.